Howdy! This is your friendly neighborhood physics teacher here, and I am here to talk about momentum, torque, and force. You have your test on Friday, so we're going to review over a few of those topics and hopefully get you to understand the questions that you might see a little bit better. Now, on the review, you have a good 2 pages of just content on things to remember. So I kind of give you the steps on how to do forces at an angle, specifically dealing with the force table lab. And then I give you things to remember about torque. And then I give you things to remember about momentum. And then it starts into the questions. So the first 2 pages are really good to read and make sure you understand. But I'm going to let you read that. I'm just going to go over the questions. So question 1. The graph below shows the velocity of a 2,400 kilogram truck moving moving during a 20-second time interval. What is the impulse implied to the car during the C interval? Now on my thing, when I copy and pasted it into this little thing I use, it did not give the C interval. The C interval for y'all is this part right there. So that is the C interval. And you're looking for the impulse in that. So remember that impulse can be force times time, or since impulse is the change momentum, impulse also can be mass times change in velocity. Now this is a velocity time graph, so we can figure out the change in velocity. If we look at the data, and we have the mass, so we have the mass of the truck. The mass of the truck is right there. The initial velocity of that part is right there, so the initial velocity is 0. The final velocity is right there, so it'll be 2. So to get your change in velocity, that's going to end up being your final velocity minus your initial velocity. So it'll just be 2 minus 0, and that'll give you a 2. So your impulse equals your mass, which is 2,400 times 2. And you plug that into your handy-dandy calculator. Helps me turn it on first. Times 2. And you get a 4,800. In this case, it's newtons per second, or the units can also be, kilograms meters per second. So it's either newton seconds or kilograms meters per second. So that's how you would use a graph to get the information to be able to find impulse. You might need to do that on the test. Hint, hint. So you're riding a horse. The combined mass of you and the horse is 240 kilograms. Y'all are running at 13 meters per second when you slow down to 5 meters per second. What is your initial momentum? So remember, momentum is your mass times velocity, but specifically asking for initial, so you're going to use your initial velocity. So your combined mass is 240, and you're starting to run at 13. So you're just going to take the 240 times 13, and that will end up being your initial momentum. Meters per second. Your final momentum, again, it's just mass times velocity, specifically dealing with the final. So your mass doesn't change, but your velocity does because you slowed down to 5. So you're going to do your mass times your new velocity, and that is now your final momentum. Final momentum. Now, to get your change momentum, your change momentum is just your final momentum minus your initial momentum. So your final momentum minus your initial momentum, and you're going to end up getting a negative number. Momentum is a vector. It just means direction. That's all it is. It's telling you that your momentum is going to the left, which makes sense because you're slowing down. So that is your final momentum. So what is your initial kinetic energy? Now, hopefully you remember that your kinetic energy is 1/2 mv squared. So it's asking for the initial, so to get your initial, you need the initial velocity. So you'd be using your initial velocity. So 1/2 m would be 240 times your initial velocity, which is 13 squared. You plug that into your calculator. So 1/2, clear, 1/2 times 240 times 13 squared, and you get a 20,280 joules. Your final, you do the exact same thing, but you're going to use your final velocity. So it'll be 1/2, mass is the same, but the velocity, you're going to use the final velocity. Plug that into your calculator. 240 times 5 squared, and you'll end up doing 3,000. And to get your change in kinetic energy, you just do, again, you do your final. So your change in kinetic energy is just your final kinetic energy minus your initial kinetic energy. So your final is 3,000. Initial is this huge number. So, of course, you're going to get a negative number. You're going to end up getting a negative 17,280 joules. That is a decimal there. So that's how you find your initial momentum, final momentum, change in momentum, initial, final, and change in kinetic energy. Oh, I forgot my joules. There you go. So give examples of actions that increase time and decrease force, and why would they be useful? So one good thing would be like an airbag in your car. So, and that would be useful because you are increasing your time. You're increasing your time that it takes you to hit the steering wheel, hit the wheel. Because before you just take like a second for you to hit. If that comes out, it kind of slows you down. So that'd be a good example of a increasing time to decrease the force. And I mean, you can talk about jumping on a mattress. You can talk about anything that adds that cushion to it. Dealing with the crumple zone of your car, seat belts, anything like that. So, a 63-kilogram cheetah is chasing its dinner. The cheetah is traveling at 31 meters per second when it realizes it will not be able to catch up to the animal, so it slows to a stop. All of this happens in about 4 seconds. What was the amount of force the cheetah was under? So let's kind of write down our givens. So we have the mass of the cheetah. We have the initial velocity of the cheetah. It comes to a stop, so that means our final velocity is 0. And we have our time, which is 4 seconds. So looking at our givens and our known, we're looking for force. Looking at our equations, we're going to end up using this equation. We have mass, our change of velocity is final minus initial, equals the force we're looking for times time, which is 4 seconds. This gives us a negative 31. So if you do 36 times negative 31, you get a negative 1953. And to get the 4 on the other side, since you're being multiplied, you have to divide. And so you get your force to be equal a negative 488 newtons. So those cheetahs, when they're having to accelerate and slow down and all that fun stuff, it's under a lot of force. It's under a lot of force. A little bit more room here. So a giraffe has a mass of about 272 kilograms. They can run up to 15 meters per second, but not for very long because of their long necks. What would be the impulse if the giraffe stops? So again, we have mass, which is 272 kilograms. We have the initial velocity of 15 meters per second, and we have our final velocity of 0 meters per second. And we're looking for impulse. We know impulse is just your change momentum, and your change momentum is mass times change velocity. So we have 272 times your final minus your initial. So it ended up equaling 272 times negative 15. You plug that into your handy-dandy calculator, and you end up getting a negative 4,080, and that'll be Newton seconds. There we go. So remember, impulse is equal to change in momentum. It's a good thing to remember. So determine the momentum of, and we have a couple of things for you to determine the momentum of. So momentum is just mass times velocity. So we have the mass here, we have the velocity there, so you just multiply those two together. So you have 9.1 times 10 to the negative 31 times 2.18 times 10 to the 6th. And that your momentum for that will end up being 1.98 times 10 to the negative 24th kilograms meters per second. And then again, so you have the mass of the bullet, you have the velocity, so you just multiply those two together. So it'll be 0.162 times 860. So I'll give you 139.32 kilograms meters per second. We have the mass, we have the velocity, you just multiply those two together. 0.2. And you hit 1,012 kilograms meters per second. Again, you have a mass, velocity, just multiply those two together. 310. And you get this really big number. Oh, put my thingy in the wrong spot. So 2, 3, 4. One more, so it should come there. Kilograms meters per second. Now, which one of the above momentums is the greatest? Looks like this, our taxi driver would be the greatest. There we go. So two friends are playing catch. One friend throws a 14-kilogram ball with a velocity of 18 meters. The other friend tries to catch the ball, but only hits it with the glove for a force of 5 newtons for 2 seconds. What is the change momentum of the glove? Of the glove? I should say the change momentum of the ball. Yeah, that's a mess up. Of the ball. Sorry about that, guys. Should be a change momentum of the ball. So let's figure out. So we have the mass of the ball, which is 14 kilograms. We have the initial velocity of the ball, which is 18 meters per second. We have the force of the ball, which is 5 newtons, and we have the time of the ball, which is 2 seconds. And we're looking for the change momentum. So we know that change momentum equals mass times change velocity. But we don't know our final velocity. So we can't use that one. So that's a no-go. We also know that our change in momentum equals impulse. And our impulse is force times time. We have force, we have time, so we can figure out the change momentum of the situation. Woohoo! So just because you always have to pay attention. If you don't have change velocity, if you don't have your final velocity, you can't use mass times change velocity. You have to use your impulse equation, your force times time. Hint, we might do this to you on the test. Hint, hint. So pay attention to that. If you don't have two velocities, you can't find the change velocity. You are in physics class working on the collision lab. You have one glider with a mass of 100 grams ready to launch, and your partner places an identical glider with the same mass in the middle of the track. When you launch your glider, it is moving with a velocity of 3 meters per second. When the launched glider hits the non-moving glider, what will the velocities be of both gliders? Well, since they have the same mass, so let's see here, we have glider 1, glider 2, 100, 100. This one is moving at 3 that direction. This is not moving. So when they collide, since they have the exact same mass, the first one is going to end up staying still, and the second one will continue in that direction at 3 meters per second. And it's because they have the same mass. It's an even transfer of momentum. So having the same mass is really easy, because think about Newton's cradle. If you pick up one ball, you drop it, the 3 in the middle don't move because it's an even transfer, and the last one goes up. You have that even transfer. You are babysitting your niece and decide to take her to the carnival. She really wants to ride the bumper cars. You go with her and let her drive. Your mass is 80 kilograms, your niece's mass is 20 kilograms, and the mass of the bumper car is 130 kilograms. You realize your niece is crazy, and she starts running into the wall at 2.3 meters per second. Luckily, it is a bumper car and rebound off the wall with the same velocity. What is the change in momentum of the system? Hint, momentum is a vector, which I misspelled vector because I'm talented like that. So, is a vector. So let's think about here. So we have mass of u, which is 80. You have mass of niche, which is 20. And you have mass of the car, which is 130. Give us some more room here. Y'all are all in the vehicle, so you have to add up all of your masses. 8, 9, 10, 11, 12, 13, 2. So your total mass of you, your niece, and the vehicle is 230 kilograms. So that is the mass we're going to end up using. So you go and you hit the wall, and you hit it at 2.3. But when you rebound, you go at the same magnitude, but rebound means you're going in the opposite direction. So your initial velocity is 23, but your final velocity is going to end up being negative 23 because you are bouncing off the wall. You are rebounding. I want to know your change momentum. So your change momentum is your mass times change velocity. Your mass is 230. Your change of velocity would be your final, which is a negative 2.3, minus your positive 2.3. You can put that into your calculator, and you're going to end up getting a negative 4.6. And you do 230 times negative 4.6. And your change momentum is still a little bumpy because it's really big. There you go. So that is your change momentum of you, your niece, the car, hitting the wall, and rebounding back. So anytime something says it rebounds, that rebounds word right there, let me highlight it, that rebounds word right there means that it's going in the opposite direction. So rebound means opposite direction. Opposite direction. So rebound means opposite direction. So if you're positive, then it switches to negative. If it's negative, it switches to positive. But there you go. So why does the cannon move when it's fired? It's more of a conceptual question, and it's because the momentum has to go somewhere. The momentum is conserved. So if you have a cannon here, and your cannon shoots, this is why most of the time your cannon, it was on wheels. So when your cannon fires, that energy that builds up here is forcing, some of it is forcing it to go in this direction. But for it to balance out, it's got to have some relief going this way. So if your cannonball is going that way, your cannon's got to go the opposite way because it's conserved. So that momentum's got to go somewhere. So what is the equation you use when two objects stick together, collide? So solve for line velocity without using numbers. So the equation, the key thing is it sticks together. So that's your key word right there. So you're going to have mass of the first object, your initial velocity of the first object, plus your mass of the second object, your initial velocity of the second object, equals mass 1 plus mass 2 divided by your final. Because it sticks, your velocity is going to be the same for both of them. You're solving for your final. So you just have to get that over. So there you go. Okay. You are trying to teach your dog to run and jump on a skateboard for a local talent show. The mass of your dog is 30 kilograms. The mass of the skateboard is 10 kilograms. Your dog runs at a velocity of 5.6 meters per second. What is the final velocity of your dog on the skateboard? Hint, this is your dog and the skateboard are going at the same velocity at the end. So you're going to end up using this equation we just solved for. So you're going to end up using your final velocity equals m1, but a lot of y'all don't. I didn't mean to make those, okay, but we're just going to use, can I write back? Thank you. So m1 v1i plus m2 v2i equals m1 plus m2 in your final velocity. So you plug in what you got. The mass 1 would be the mass of your dog, which is 30, and the initial velocity of your dog would be 5.6. The mass of the skateboard is 10. Well, at the beginning, it's not moving, so it'd be 0. Then you do 30 plus 10, and you're trying to figure out how fast the objects are going together, the dog and the skateboard. So 0 times 10 is just 0. 30 times 5.6 is 168. And then you just do 30 plus 10, which gives you 40. To get your VF by itself, you have to divide. So you get that your VF equals 4.2 meters per second. Woohoo! Okay, since you are an amazing physics teacher, they let you and your partner since you have amazing physics teachers. I can't read. They let you and your partner go on a seesaw. The only catch is you have to find out where y'all sit to balance the seesaw. Your partner is lazy and sits on the edge with a mass of 80 kilograms of a 10-meter long seesaw. Now you have to do all the work to figure out where you need to sit to balance a seesaw. You have a mass of 50 kilograms. So let's draw a little seesaw out. You have lazy boy over here, or lazy girl, lazy human being over here, and they have a 80 kilogram, and you need to figure out where you need to sit over here. And you have a mass of 50 kilograms. And it says that the whole entire thing is 8 meters. So if they are sitting on the edge, that means they are 4 meters from the pivot point. And we don't know how far you need to sit. So this is where the torque comes into play. So you do torque of what would spin anti-clockwise would have to equal the torque that would spin clockwise. This side is going down, so if it could rotate all the way around, that would end up being anti-clockwise. The same thing here, this was going down, and it could spin all the way around, that would end up being clockwise. So your force times your distance equals force times your distance. But we don't have force, we have mass. So mass times your acceleration due to gravity times distance equals mass times acceleration due to gravity times distance, because what's pulling it down is the force of gravity. Since you have acceleration on both sides, you can just cross out your acceleration, and just do mass times your distance, mass times your distance. So you can take 80 times the 4, because you know that's where your partner's sitting, they're not moving, and then it'll be your mass and whatever distance you're trying to figure out. To get distance by yourself, you just divide. So the distance you would need to sit to balance it out, 80 times 4 divided by 50, you would need to sit 6.4 meters away. So AKA, in this case, you wouldn't be able to balance it out. It's not possible. Where he sat, can't balance it. It's not possible. But that's okay. That's how you would do that. Now, let me erase this word here just so we can see what's going on. You will have a question that is pretty much using this chart. A question just using this chart. You'll either have to find, you would either be doing a 2-force, or you'd be doing a 2-force or 3-force vector. One will be, the 4-force would be extra credit. The 3-force would just give you the same amount. I believe the extra credit is 5 extra points. And if we refer back to the steps that were at the beginning, the first thing you need to do is to get the mass to the force. And do that, you're going to multiply. So we're going to kind of do this. So to get from mass to force, you're going to multiply by 9.8. So you're going to multiply all your masses by 9.8. You have a mass of 2.9 and you have a mass of 2.4. So you have 0.29 times 9.8, and you get a 2.84, and your 0.24 times 9.8, and you would get a 2.35. You you'd plug that information into your chart. Now, to get your velocity in the x, so velocity in the x. Hopefully you noticed in your homework, like doing all this, that you can actually just use the force of your x equals the force that you just solved for times cosine of whatever angle we give you. You can use these big angles. It's okay. And I totally wrote these in the wrong spot. I just realized that. Sorry about that, guys. Let's try that again. So 2.84 and a 2.35. So to solve for your force in the x, you would just use your force that you solved for, 2.84, cosine of whatever angle they gave you, which was 121. You plug that in your calculator. Make sure your calculator is in degrees. To do that, hit mode and make sure degrees is highlighted. Then you just type in, so 2.84 times cosine of 121, and that'll give you a negative 1.46 newtons. So you would plug that in, a negative 1.46. You can do that for the same one again. So it would be your force times cosine of your angle. In this case, you would use your other force, which is 2.35, cosine of the angle for the next one, which is 339. You can plug it in. So 2.35 times cosine of 339. Plug that into your calculator, you get a 2.19. You just plug that in right here. Nope, wrong spot. A 2.19. So that is for your force in the x. So your force in the y, you're going to use, again, your normal force and just do sine of your angle. So it was 2.84. Sine your angle was 121. You would plug that to your calculator. You do the same thing for the other one also. Sine of your angle, your force over here was 2.35. Sine of your angle, which was 339. There's your force in the y. And let the calculator do the hard work for you. So 2.35 times sine of 339, you would get a negative 0.84. And then this one, 2.84 times sine of 121, and you would get a 2.43 newtons, of course. Newtons there. And you would just plug in the information up here. So that's 243, 2.43. And this one is negative 0.84. For your next one, you're going to solve for your resultant force in the x and your resultant force in the y. To do that, you're just going to add up your forces in the x, add up your forces in the y. So basically, you're just going to add these two together, and you're going to add these two together. So you're going to add 2.19 plus the negative 1.46, and you're going to add the negative 0.84 plus the 2.43. So you would get 2.19 plus a negative 1.46, and you would get a 0.73 for your resultant force in the x, and you do a negative 0.84 plus 2.43, you get a 1.59 newtons, of course. So that is your resultant force in the x, which was 0.73. This is your resultant force in the y, 1.59. The next thing we would want to solve for is your resultant force. So your resultant force. You're going to use a squared plus b squared equals c squared to solve for that. Your a squared, you can use your resultant force in the x plus your resultant force in the y, and you're going to be solving for your resultant force. It doesn't matter which one you put, a or b, you just need them in there. So it'd be 0.73 squared plus 1.59 squared equals your FR squared. To get rid of the squared, you're going to square root all of that. You can actually plug it into your calculator that way. So you do the square root of 0.73 squared plus 1.59 squared. Make sure you end your parentheses, and your resultant force is end up going to be 1.75 newtons. That's what you do here, 1.75. Point is not. Oops. Okay. So from here, you can actually, so here, it's actually going to be the exact same thing for your resultant, your equilibrium force. So your equilibrium force equals your resultant force. So your equilibrium force in this case would just be 1.75 newtons. So your equilibrium force and your resultant force is the exact same. Then you can figure out your mass. Figure out your mass. Do that, you're just going to use F equals ma. In this case, you're using force of acceleration due to gravity because it's a force of gravity. So your mass is just going to be your force divided by your acceleration due to gravity. Your force is 1.75, acceleration of gravity is 9.8. So you get 0.7 or 17, sorry, 0.179 kilograms is your mass. And since the forces are same, it's the same mass, 0.179, 0.179. So those end up being the same. So these end up being the same, and these end up being the same. Now to find your angle. Now to find theta, to find your angle. That's when you have to draw out your triangle. So you're going to go back to your resultant your resultant in the x and resultant in the y. They're both positive, so this one's going that way and this one's going that way. Always draw your x first, then your y. Makes life a whole lot easier. And so that becomes your resultant. So that becomes your force, your resultant force in the y, your resultant force in the x, and that is just your resultant force. And that would be your angle. Because that is your hypotenuse, this is your opposite, this is your adjacent, you can actually use your tangent. And you're going to use your inverse tangent because you're looking for your angle. So it'd be FRY over FRX. Your FRY was 1.59. Your X was 0.73. And you plug that into your calculator. So you would literally put second tan and be 1.79 divided by 0.73, and you get a 65.34 as your degree. You always want to double check and make sure that you don't need to do anything fancy in your quadrants. So this is 0, 90, 180, 270, 360. So you drew your in this was your angle. So you are set because that 65 degree makes sense. So that is your answer. Scroll up all the way up here. So 65 degrees is your angle. But to solve for your equilibrium angle, you'd be pulling that way. So we need to do an additional 180. So to solve for your equilibrium angle, you're going to take your resultant angle and add 180. So it'd be 65 plus 180. And you get a 245 degrees as your resultant, as your equilibrium angle. And these will actually end up being the same numbers. What color haven't I used yet? I haven't used yellow. These will end up being the same numbers, just since you're in quadrant 3, though. This becomes negative, and this becomes negative. So your degrees end up flip-flopping, but it's the same number. So there you go. That's kind of the process for it. So yeah, if you would want me to help you with four vectors and 5 vectors, you're more than welcome to come in for tutoring. I will post the key to those two with the video. I just don't want the video to get extra long by me working two more problems, but it'd be the exact same setup, just doing it again for 3 vectors or 4 vectors. If you have any questions, please ask Miss Verona or Miss Heath. Hopefully you have a wonderful day. Happy studying. Bye!